Hello and welcome to Part 6, Lecture 1, Survival Analysis. In this lecture, we will be addressing parametric survival analysis. So what if the study you wish to perform involves time as a variable of interest? For example, one of two protective creams was applied to the arm of each person in a study. A painful irritant was added to the same arm. Now for cream A, out of 19 subjects, 17 experienced pain, and 2 at the time of last recording still had no pain. Cream B, on the other hand, had 13 people who experienced pain, and 6 who at the time of last recording still had no pain. So in this case, let's say your outcome is pain, no pain. That could be logistic regression, correct? However, you may be interested in the concept of time, right? The dimension of time, where you're going to say, well, at the time of last recording for cream A, we had 2 people who didn't have pain, and for cream B, we had 6 people who still did not have pain. But we do know that the longer we wait, the higher the chances are that they're going to feel pain, and we're actually interested in knowing how long that takes, or if the length of time would affect the effectiveness of the 2 creams. How about another example? Let's talk about survival. If we're comparing time to death based on 2 drugs for cure, if drug A, time to cure for 17 people, but 2 people were still alive at the time of last recording, and drug B, we had cure for 13 people, but at the time of last recording, we had 6 people still alive. So same idea. In this case, we could simply model death, yes, no, in a logistic regression. However, we would lose then the concept of time and the importance it plays in your outcome. Let's have a look at an example. In this case, I'm going to look at comparing the time to an event, so time to event. In this case, the event is headaches. So you will see on the top half of the slide here is the data set. It's called headache. We have, of course, our outcome, which is time in minutes. We have our group, and we have now a censor, what's called a censor. So what does a censor mean? The censor is simply a binary variable that indicates whether or not a given subject has been censored. And when you have what's called a right censor, which is most of the time, it means that the participant is no longer available for measurement. And for various reasons. It can be that they left the study. It could be that they no longer want to participate in the study. It just simply means they're not available for measure, and we don't know why. It doesn't mean that the event occurred. It means that we can no longer get any more data on them. So they are what you would call censored. Now, on the lower half of the slide, I'm giving you a whole bunch of PROC means, and this is just to look at the different means between your grouping variable and also between those subjects that have been censored. Here's your output simplified from your PROC means. So the first one is for all subjects. So we have 38 in all. We have an overall mean of 22 minutes. And then when we look at the difference in, well, the means from the 2 groups, we have group 1 and group 2. We have a mean of 20.6 for group 1 and a mean of 23.5 for group 2. So just looking, at the means, we can see that group 2 has a higher mean time. Now, When looking at the group differences by censor, we'll see here that when patients have not, or subjects, sorry, have not been censored, and we look at the two groups, we have 17 and 13. So that's the majority, right? So the majority of patients or subjects have not been censored. If you look at the difference in the means between the groups, it's similar-ish, right? So you have 20.4 for group 1, and you have 21.6 for group 2. However, if you look at those patients, subjects that have been censored, so meaning they're at a given moment in time, they are no longer available for measurement, you have two smaller groups. Group 1 only has two patients or subjects with a mean value of 22.5, and Group 2 has 6 subjects with a mean value of 27.5. Let's get to the analysis. Now, I encourage you all to perform a simple t-test on your outcome, which is time in minutes between the two groups, and then you can compare it to what we get here with survival analysis. Now, in this case, we are starting off with what's called parametric survival analysis, and we use a procedure in SAS called LIFEREG, reg, of course, for regression. And inevitably, you will recognize immediately that it looks very much like PROC GLM, PROC General Linear Model. And for good reason, because we are performing regression. Now, there are a few differences, and one is your outcome is, of course, minutes, so your time in minutes, but you need to tell SAS whether or not for each subject, whether they were censored or not. And so you do so by including it here with your outcome, and you put the variable, which we named censor, which makes sense, that's going to indicate whether or not the subject was censored. And then you tell SAS what, did you use in order to identify as censored or not. And so in this case, we're saying 1 in this variable called censor means that the subject was censored. Okay, that's pretty straightforward. If you look at the outcome, the output over here, I'll just point out a couple of things. One is you see here the dependent variable is minutes, and oh, it's been logged. And so you guys say, well, why would I log it? Well, it's because in order to perform parametric modeling for survival analysis, you need to linearize your equation, and to do so, you have to take the log of your dependent variable. And we're not going to go into detail on that, but we'll touch on it a little bit. You'll see the number of observations was 38, the non-censored values was 30, there were 8 right-censored values. And they'll just automatically put the other type of censoring that's possible, which would be left censored and interval censored values, which we're not going to talk about in this lecture. We're just going to talk about right censored, which is the most common. You have your number of parameters, of course. The name of your distribution. So whenever you do parametric modeling, you have the option of choosing the distribution for your functions. And SAS here has defaulted to the Weibull distribution, and we're not going to go into detail on all the various distributions and what the appropriate fits are. But just to tell you that SAS will default to Weibull if you do not choose one. Okay. So if we use the data set with all 38 subjects, this looks very familiar to you, right? Your type 3 analysis of effects. So meaning, is your group variable significant in the model? And it certainly is. If you look down here at your parameter estimates, of course, here's the same p-value for your chi-square test for group. No surprise, it's the same here for your type 3 analysis of effects. Because it's the only variable in the model. For now, I'm going to skip over these two parameters, which are called the scale parameter and the Weibull shape parameter. And that's why in the previous slide, it said how many parameters we're estimating. Well, we're estimating 3, because you have your group, you have your scale, and you have your Weibull shape. And these two parameters are required in order to do parametric modeling of survival data. So when we use all of the subjects, we get a significant difference in time between mean time between the two groups. But what if we did not want to consider those subjects who were censored? Let's just simplify. So we run the same analysis, but you see here in the data step, we just only include those subjects who were censored as 0, meaning that they're not censored. And if you look at that, you'll see now we only have 30 subjects, and there's no significant difference in mean time between the groups. And you'll remember that the two means were actually quite similar between the two groups, and it was 20 minutes and 21 minutes, or 21.6 minutes. Of course, to be thorough, we should perform the same analysis on the patients or subjects who were censored. In this case, we have 8 subjects. So you'll see here in the data step, sorry, I'm just getting my pointer. We have if censor equals 1, which means only include those subjects that have 1 as for their censor variable. We run the same PROC LIFEREG analysis, and we end up with a significant difference between the two. Now, that's not super surprising, because if you remember when we did PROC means, the mean time between the two groups for those who were censored was larger, 22.5 and 27.5. So what's the value of censored data? Now, as I'd asked you guys to perform a t-test on this data to just see if the mean time between the two groups was significantly different. But if you had tried doing that, you would have bumped up against the problem with, what do I do with those 8 subjects who were censored? Do I just include their times? Do I just roll it in? Or do I exclude them because I'm not comfortable with the idea that survival times in which the event did not occur is just weird? And if you had chosen, which would probably be the right choice, to exclude those 8 subjects, you would have found a p-value that was not significant. However, if you perform this survival analysis, so this parametric survival analysis, in which you account for censored observations, then you end up with a significant finding. And there's the value of performing survival analysis when you have censored observations. So, as always, we need to, talk a little bit about math. I'm not even going to touch on the equations, but what I am going to say is, in survival analysis, there are basically 3 functions you should be aware of. One is a survivorship function, and it's simply the probability of surviving past a given time. So event-free past time t. It's a probability, it must be positive, and of course between 0 and 1. The probability density function, PDF, is the unconditional probability that the event will occur at an exact time. It must be positive, of course, and between 0 and 1, because it is an unconditional probability. And lastly, the hazard function. Now, the hazard function is the instantaneous risk that an event will occur at a given time, given no event up to that time. So it's conditional. Now, the hazard function is a risk. It's an instantaneous risk. It is not a probability, and therefore it can be greater than 1, but it must be positive. When using PROC LIFEREG in SAS, we are performing parametric survival analysis, and the reason for this is because we're using a general parametric model, just like PROC GLM, as we pointed out in previous slides. Now, in order to be able to work with censored data, SAS uses what's called an accelerated failure time model, and this is just simply a way to linearize the model by taking the logs. Here's the equation here. It is very similar to what we've seen in the past. The error term is a little different, and your outcome is the log of time. Now, time, of course, is the failure time for your subjects, and it's modeled as a function of your covariates. Now, as I explained earlier on, there are different distributions that you can use for this function, for this model. And here is an example of a bunch where you have yBull, which, as I said, is the default. It's also costly because you are estimating 2 parameters. You also have the exponential distribution, a gamma, a log logistic, log normal. And all of these distributions are useful because you need to find or you need to know which of these distributions best fits your data. So what are the advantages of parametric modeling and survival analysis? Now, in the previous slide, we mentioned that you need to make assumptions about the shape of your distribution or your hazard function or survival function. And if you make the correct assumptions and your data fits the distribution that you have hypothesized, then you have a strong model. But if you have if you guess the wrong shape, if you hypothesize the wrong distribution, then your model is poor. It's extremely poor. And so there is probably the strength of parametric modeling and the disadvantage at the same time is that if you choose the wrong distribution, then your model will end up being poor. Now, other related advantages, of course, is that more efficient estimates will be provided if the shape of the survival distribution is known. So meaning that you a priori know the distribution, and therefore you can perform strong parametric modeling. Regression coefficients can be clinically meaningful and can be related to those from a Cox proportional hazards model, and we'll talk a little bit about that later on in the course, which is often something that is used in, or a method that's often used in medicine for survival analysis. Now, of course, it may sound silly, but parametric modeling actually can provide you with estimates of time, of survival time. So if you are interested in actually obtaining an estimate of time, then parametric modeling is what you need to do. Some of the other advantages are less impactful in the sense that residuals can be computed. So that's something that you may want to look at, right? The differences between observed and predicted survival times. And importantly for us, and we can control for confounding variables, and we've seen a lot of that in this course. And so this is just an extension to that. So that brings us to the end of our first lecture in survival analysis. And in the next lecture, we're going to talk about life test or PROC life test, which is a non-parametric way of modeling survival data.